Hello, welcome to another Chemistry to Go podcast. Glad you're back with me, and we'll get started on acids and bases. So we'll talk about some properties of each first, then we'll get into some problem-solving type stuff. And let's first start with properties of acids. They are reportedly, and there will be some exceptions to this kind of stuff, but I'll give you some of the more general concepts here. They taste sour. They contain the hydrogen ion, H1 positive ion that is, have a pH less than 7, react with bases to form a salt and water. That's called a neutralization reaction. We'll discuss a little bit about that later. They react with some metals to produce hydrogen gas. As far as indicators go, one of the simplest indicators that most everyone, by the time they've reached high school, has at least some familiarity with is litmus paper. Litmus paper can be either red or blue, though it's not truly a red color or truly a blue color. Those are the common names for them. And if you dip either color litmus paper into an acid, it will turn red. Again, not a true red, more of a pink, but all purposes set aside, it's red. Some other indicators that you may or may not be familiar with are phenolphthalein. It is a solution that is colorless on its own, and when dropped into an acid it remains colorless, so it's really hard to tell whether the phenolphthalein is in there or not. Bromothymol blue is another one that is a solution. It is blue on its own. When it's dropped into an acid, it will turn the acid yellow. And we tend to find acids in fairly common everyday items like citrus fruits, things like lemons and oranges that have citric acid. And hope you don't encounter these too often, but soured milk and sore mussels also contain acid, and that is called lactic acid. We also find acid in vitamin C, which is called ascorbic acid. And lots of folks, of course, drink carbonated beverages. Well, what makes them carbonated is the presence of carbonic acid. It's the same stuff that comes out of your mouth as you exhale. You exhale water and carbon dioxide, and when we combine those two, we get carbonic acid. You'll also note on a lot of soft drink cans, carbonated beverage cans, it'll say that they contain phosphoric acid too. Some properties of bases include that they taste bitter. They tend to contain the hydroxide ion, which is OH, 1 negative ion. Their pHs tend to be greater than 7. They also form neutralization reactions with acids to form a salt and water. And they, unlike acids, really like to react with organic material. Well, one of the reasons we know they like to react with organic material is that when we touch a base, we will report that our fingers feel slippery, that the base feels slippery. The reason for that is because it's actually working on an outer layer of skin and kind of doing away with it. They, as far as some of the same indicators go, will turn litmus paper blue. Phenolphthalein, again, which is colorless on its own, will turn fuchsia, a hot pink color in the presence of a base. Bromothymol blue, which is blue on its own, will stay blue in the presence of a base. We tend to find bases in drain cleaners. Remember, they like to react with organic materials. Well, what tends to clog a drain but organic stuff like hair? So if you drop a base down a clogged drain, typically in the form of sodium hydroxide, it will react with the organic material in that drain rather than the metal that the drain might be made of and do away with your clog. It is also found in ammonia-based cleaners, things such as Windex. And let's see, a final component or substance of which a base is a component is soap. Oftentimes lye, which is sodium hydroxide, is used to make soap. There are 3 very different, in essence, ways to classify acids and bases. The first of them is known as the Arrhenius method. So named for a Swedish gentleman named Svante Arrhenius, who put forth his definitions of acids and bases at the age of 25 in the late 19th century. He did receive a 1903 Nobel Prize in Chemistry for his discoveries on electrolytic dissociation. Just a little cocktail information there. Arrhenius defined an acid as a substance that will dissociate in water to yield a hydrogen ion. Well, I kind of already gave that as a property of acid, so that one's almost a no-brainer. Most of us tend to already know that, just not necessarily that it's Arrhenius's definition. He defined a base, you guessed it, as a substance that will dissociate in water to yield hydroxide ion. So we have a couple of other methods of classifying acids and bases that are a little more complex and do a little more for us and allow us to classify things that, according to Arrhenius, would not have necessarily been acids or bases, but really do behave as acids and bases. So one of those methods is known as the Bronsted-Lowry method. Danish gentleman Johannes Bronsted and English gentleman Thomas Lowry came up with this way to classify acids and bases and their conjugates. Acids and bases, according to Bronsted and Lowry, are always going to be reactants. Conjugates, conjugate acid, conjugate base, will always be products. And they did this work in the 1920s. Never received a Nobel Prize for furthering the concepts, and Arrhenius never accepted their definitions. I'm sure they had little tete-a-tetes with each other. So let's go to their classifications. Bronsted-Lowry, acid is a reactant that donates a proton in a chemical reaction. They defined a base as a reactant that accepts a proton in a chemical reaction. A conjugate acid, I'm going to define in two ways, because you can look at it in two ways. You just decide which way works better for you. A conjugate acid is a product that is formed when a base accepts a proton. And another way to look at that is that if we were to reverse the reaction, because these will always be reversible reactions, then the conjugate acid will donate a proton. That is in the reverse reaction. They defined a conjugate base as a product that is formed when an acid donates a proton. You can think of it as what's remaining after the donation of the proton has occurred on the reactant side. And an alternate method of defining it is that in the reverse reaction, the conjugate base will accept a proton. So a third method, and I'm going to give you examples of each of these in just a bit, is Lewis acid-base classification. Yep, it's the same guy who did the Lewis electron dot structures. He's a little obsessed with electrons and electron pairs, in my opinion, but I certainly thank him for Lewis dot structures because they do make us make a lot of sense out of things. The Lewis acid-base stuff is just not as widely used, but I feel that I need to at least expose you to it, just so I've covered all of my bases. You get it? All of my bases. Okay, stop laughing now. Alrighty, a Lewis acid is a reactant that accepts an electron pair. Now remember, Lewis is a guy obsessed with electrons. Bronsted and Lowry worked around the same time Lewis did in coming up with these definitions, and they said that an acid is a proton donor. Well, protons and electrons tend to occur in opposition to each other, so it should make some sense to you that if an acid is defined as a proton donor, that it would also be classified as an electron pair acceptor. If that helps, hopefully you'll use it. And Lewis defined a base as a reactant that donates an electron pair. Again, think of how Bronsted-Lowry defined a base as a proton acceptor. If it's willing to accept protons, it ought to be willing to donate electrons. Alrighty. I want you to write a reaction, and if you're looking at my PowerPoint, it's already there for you. But write a reaction where you have HCl, it's aqueous, reacting with liquid water in a reversible reaction to make H3O, one positive. It's called the hydronium ion that's aqueous, and chloride ion, Cl1 negative, that's aqueous. What we're going to do is classify each of these according to Arrhenius and Bronsted-Lowry. So, as we look at that reaction, according to Arrhenius, when I look from left to right, the HCl changes into something that doesn't have a hydrogen ion in it, meaning you look at the chloride ion on the right and it's missing its hydrogen ion. Well, that's because HCl donated a hydrogen ion. That is the Bronsted-Lowry way to look at it. The Arrhenius way to look at it is that it yielded H3O1 positive. Well, all H3O1 positive ion is water with a hydrogen ion. And all a hydrogen ion is a proton. So really, Arrhenius' definitions and Bronsted-Lowry's definitions of acids work together. If you look at the H2O, it's a base according to Bronsted-Lowry. It's not a base according to Arrhenius, because remember Arrhenius said we have to have hydroxide ion. Well, that's just where his method really doesn't work that well. Bronsted-Lowry defined H2O in that particular reaction as a base because when we look from left to right side, H2O becomes H3O, 1 positive, which means that it accepted a hydrogen ion, which is also a proton from the HCl. So again, the HCl is the acid, the H2O is a base. When we look on the right side, we can use the Bronsted-Lowry definitions of conjugate acid and conjugate base to figure out which is which. So as I look on the right side, H3O, 1 positive, is what is made when the water accepts a proton. That makes it the conjugate acid. If I look in the reverse reaction, H3O, 1 positive, will donate a proton and make H2O. That, again, makes it a conjugate acid. So either way we look at it, it's a conjugate acid. The Cl1 negative ion is a conjugate base because of either definition. It's what's produced when the HCl donates its proton, meaning it's what remains when the HCl gets rid of its H ion. Or in the reverse reaction, it will take on a hydrogen ion to form HCl. So either way, it's a conjugate base. Now if you write the following reaction, ammonia, which is NH3 gas, plus H2O liquid, yields in a reversible reaction ammonium ion, which is NH4, 1 positive, aqueous, plus OH ion, which is OH, 1 negative, hydroxide ion, and that's aqueous. Then we'll address it in the same manner. The NH3 is a base because when we look from left to right, it accepts a proton. It goes from NH3 to NH4, 1 positive. And again, that's according to Bronsted-Lowry. It's not a base necessarily at this point according to Arrhenius, but we'll kind of toy with that in just a moment. H2O is classified as an acid. According to Bronsted-Lowry, it donates a proton to the ammonia, and it's left as OH, 1 negative. So it's a Bronsted-Lowry acid. Now if I go back and address the Arrhenius issue there, then I might be able to state that the ammonia, the NH3, is a base because it does kick out OH, 1 negative ion. But it's really hard to see in there, in that reaction, that the OH ion came from NH3 because it really didn't. It came from the H2O. So I find that to be very confusing with Arrhenius's definition. And we'll pretty much stick with Bronsted-Lowry definitions of acids and bases. They are the most logical and the most widely used. So continuing with this example, NH4, 1 positive, is classified as a conjugate acid because it's produced when the ammonia accepts a proton, or in the reverse reaction, it will donate a proton, give up a proton. And the OH, 1 negative is a conjugate base, according to Bronsted-Lowry, because it's produced when the water donates a proton, meaning it's what's left, or in the reverse reaction, it'll take on a proton. Did you happen to notice that water behaved as a base in the first example and as an acid in the second example? That means water is an example of a substance that can behave as either an acid or a base. We call those substances amphoteric, A-M-P-H-O-T-E-R-I-C. Another name is amphiprotic. And what that means is just it can go back and forth from being an acid to a base. It just depends upon its circumstances. Just to give you an example of Lewis acid-base theory, if you will draw the Lewis structure for ammonia, which is NH3, you should see that you have single bonds emanating from the nitrogen to the 3 hydrogens. And that nitrogen has a lone pair of electrons on it. I want you to react it with hydrogen ion, which has a 1 positive charge. That 1 positive charge means that it gave up an electron, while hydrogen only had 1 electron to begin with. So it's just written as H, 1 positive. It has no dot. And according to Lewis, an acid is an electron pair acceptor, and a base is an electron pair donor. Well, the easy way to do Lewis acid-base stuff is to look at your reactants and see who has an electron pair that it might be willing to share. Well, I think you can clearly see if you've drawn what I've asked you to draw, that NH3 has that lone pair that it's willing to donate to the hydrogen. And in so doing, it forms NH4, 1 positive, which is the ammonium ion. So we would classify NH3 as the Lewis base because it donated the electron pair, and hydrogen ion in that example as the Lewis acid because it accepted an electron pair. Every acid and base that we write will be written as dissociating in water. Even water, since it can behave as both an acid and a base, is going to be dissociated in itself, essentially. So everything will end up being aqueous on the product side is what that means. The dissociation of water that we'll use repeatedly is H2O liquid, forms in a reversible reaction, H1 positive, that is aqueous, and OH1 negative, that is aqueous. Now what I'd like for you to do is realize that that equilibrium stuff that we had gone over is coming back to haunt you. Oh, yeah, no, quit groaning. So I want you to write the K expression for that reaction I just gave you. I want you to keep in mind that we only include gaseous and aqueous phases in a K expression. We always exclude liquids and solids. Remember that it's always the concentration of the products raised to the power of their coefficients divided by the concentration of the reactants raised to the power of their coefficients. So what I end up getting then is a K value that is K equals hydrogen ion concentration raised to the first power divided by hydroxide ion concentration raised to the first power. Notice the water is not present because the water is a liquid. What you've just written is called the autoionization of water's equilibrium expression. It's known as a KW. Write an uppercase K for the equilibrium constant with a subscript of W, obviously representing water. That KW expression will help you do so many things as we go through acids and bases. And just as any K value indicates the preference to make reactants or products based upon how big the K value is, we can look at the K value of water at 25 degrees Celsius, realize that it is 1 times 10 to the negative 14th molarity squared. It's a very small number. It's considered a small K value. And you might recall, hopefully you do recall, that small K values, those less than 1, prefer to make reactants at equilibrium. Which means we solve it using an equilibrium chart when we start to discover equilibrium reactions of acids and bases. It's pretty nice. What I do want you to keep in mind, by the way, is that a K value changes as temperature changes. Well, since this is a KW value, it will also be able to change as temperature changes. The value that I've given you, 1 times 10 to the negative 14th molarity squared, holds true only at 25 degrees Celsius. If I change the temperature, I change the K value, and that's going to create an explanation for something in just a few minutes. So what I want you to do now is make an equilibrium chart for that autoionization of water, that dissociation of water. Remember, you had H2O liquid yields in a reversible reaction, hydrogen ion that's aqueous, and hydroxide ion that's aqueous. Now remember that we exclude liquids and solids, which means you can write H2O in your equilibrium chart, but you're not going to have any values sitting beneath it in that column. In an equilibrium chart, you have initial change in equilibrium as your row headings. Initially, as with any products, we don't have any concentration because we're assuming the reaction hasn't yet begun. So your initial line for your hydrogen and hydroxide should read 0 and 0. From your work with equilibrium reactions, I think you know that they have to go up. Those two concentrations have to go up. But this is an equilibrium chart, therefore we don't know by how much they go up. We know it's some amount of X. We let the mole-to-mole ratio guide us. So we should realize that hydrogen's concentration is going to go up by 1x, as is hydroxide ion's concentration. So your change line should read underneath hydrogen ion and hydroxide ion plus 1x plus 1x. At equilibrium, that means we will have x for the concentration of hydrogen ion and x for the concentration of hydroxide ion. Now I want you to determine the equilibrium concentrations of both the hydrogen ion and the hydroxide ion at 25 degrees Celsius. And all you're going to do is what you've done in the past, plug into a K expression, so that you will have 1 times 10 to the negative 14th molarity squared equals x raised to the first times x raised to the first. That means 1 times 10 to the negative 14th molarity squared equals x squared. When you take the square root of both sides, you get x equals 1 times 10 to the negative 7th molarity. Well, lo and behold, you have found the equilibrium concentrations of both the hydrogen ion and the hydroxide ion. And gee, they are equal. And that is going to be a very potent concept, because when the hydrogen ion and hydroxide ion concentrations are equal in any solution, whether it's just water or something dissolved in water, we can state that that solution is neutral. That is the only time we can definitely state that a solution is neutral, is when the hydrogen ion concentration equals the hydroxide ion concentration. And the true definition of stating whether a solution is acidic or basic is comparing those concentrations of ions. If the hydrogen ion concentration is greater than the hydroxide ion concentration, we can say it's acidic. If the hydrogen ion concentration is less than the hydroxide ion concentration, we can say the solution is basic. And that is the truest definition of acidity and alkalinity that you can have. pH is what we tend to use, but I'm going to tell you in just a bit, pH really can change too much, and it's too temperature dependent. You're getting a little foreshadowing there. We will be able to determine, using the K expression, hydrogen ion concentrations and hydroxide ion concentrations. If we know a substance's hydrogen ion concentration, we can find its hydroxide ion concentration and vice versa. I'm going to throw in the concept of pH at this point because it is so universally used. I just want you to get to where you understand how inaccurate a lot of folks' understandings and definitions of pH really are. pH stands for the power of hydrogen. It's written with a lowercase p to represent power, and an uppercase H is the symbol of hydrogen. And we calculate pH by taking the opposite logarithm of the hydrogen ion concentration. So pH equals the negative log of the hydrogen ion concentration. Alright, so you just calculated the hydrogen ion concentration of water at 25 degrees Celsius, and you calculated it to be 1 times 10 to the negative 7th. If I take the opposite log of 1 times 10 to the negative 7th, and you need to really work with your calculator on this and just make sure you're getting the same numbers that I'm getting to figure out how to use log base 10 on your calculator. Remember, this is the LOG button, not the LN button. Natural log is a totally different concept, so make sure you're using the LOG button. And if I take the negative log of 1 times 10 to the negative 7th, I'm going to get 7. Now you should just have an aha moment right now where you go, well, sure, water has a pH of 7. I know that. It's neutral. But are you noting that I keep throwing in at 25 degrees Celsius? And I told you that the K value can change as temperature changes. What that means is the only time that water is guaranteed to have a pH of 7, and exactly 7, is when it is at exactly 25 degrees Celsius. If the temperature changes, the pH of water changes. So I have never liked the definition that something is neutral when its pH equals 7, because it's all temperature dependent. I prefer the definition that something is neutral when its hydrogen ion concentration equals its hydroxide ion concentration. Now if we want to work backwards and already know the pH of something, then we can find the hydrogen ion concentration. And what we essentially do is kind of flip-flop the pH equation that I just gave you and have it read hydrogen ion concentration equals 10 to the negative pH power. If you look on your calculator, your second function of your logarithm button is 10 to the x. Well, what it's doing is taking 10 and raising it to the power that you tell it. So if I know that the concentration of hydrogen ion was 1 times 10 to the negative 7th, I took the negative log of that value, I got the pH to be 7, then I plug in my pH into this equation, and 10 to the negative 7th is really the same thing as 1 times 10 to the negative 7th. I do want you to write the mantissa even if it is 1. I don't want you to just write 10 to the negative 7th. So another concept that's not as widely used as pH is POH. And as you might have already guessed, POH stands for the power of hydroxide. So this is going to all sound like familiar territory to you. To find the POH, you take the opposite of the logarithm of the hydroxide ion concentration. So pH equals negative log of OH ion concentration. Now remember, you also found the OH ion concentration of water at 25 degrees Celsius. And you knew that it is 1 times 10 to the negative 7th molar. If we take the opposite log of that same number we already did, we get the POH to be 7 as well. So what that means is at 25 degrees Celsius, the pH of a solution plus the POH of a solution that is aqueous will be 14. The sum of the pH and POH for any aqueous solution at 25 degrees Celsius will be 14. And that's where you've probably gotten the notion that the pH scale ranges from 1 to 14, some folks tell me, from 0 to 14, some folks tell me. And again, you've been lied to. I'm sorry to break the news to you again. The pH scale does not just stop at 14, and it doesn't just stop at 1, and it doesn't just stop at 0. It can range above 14, and it can be below 0. And again, if I change the temperature, I change what that sum of the pH and POH will be. It's just a convoluted little world, isn't it? Okay. So, what you can do now is I can give you a problem where I give you one bit of information and I ask you to find 3 or 4 other bits of information. So let's try a practice problem. I want you to find the pH, the POH, and the hydroxide ion concentration. State whether the solution we're talking about is acidic, neutral, or basic. If we know that the hydrogen ion concentration has a value of 3.48 times 10 to the negative 4th molarity. Well, you've got several things to find, and you may do it in whatever order you wish to. I'm going to go over several ways to do it. Okay, I'm going to choose to find the pH first because that's just a no-brainer. I'm just going to plug into my pH equation where pH equals the negative log of the hydrogen ion concentration, so I plug in pH equals the negative log of 3.48 times 10 to the negative 4th. When I work that out in my calculator, because I'm not making you use log tables, I'm sorry, I'm old enough to have had to use log tables and I didn't like using them, and I don't think you would either. But when you take the negative log of 3.48 times 10 to the negative 4th, you get pH equals 3.46. Now notice that at this point, I could go ahead and state that it's acidic because its pH is less than 7. And the assumption I'm making here is that I'm at 25 degrees Celsius. I'm not going to throw you by putting things at different temperatures and not telling you. So we can go ahead and state that this is acidic. The POH I can also find pretty easily here. If I know the pH is 3.46 and I know that pH plus POH equals 14, then all I have to do is take 14 minus 3.46, which is my pH, and I get 10.54 as my POH. Well, now I can find the hydroxide ion concentration. And I can do so in a couple of ways. I'm going to go over both ways. One way is to use the KW expression. That one's always going to be there for you. KW equals the concentration of hydrogen ion times the concentration of hydroxide ion. KW, again, I'm not changing the temperature, has a value of 1 times 10 to the negative 14th. In this case, you know the hydrogen ion concentration is 3.48 times 10 to the negative 4th, and you don't know the hydroxide ion concentration. It's a simple algebraic solution. So you take 1 times 10 to the negative 14th divided by 3.48 times 10 to the negative 4th, and you get the OH ion concentration to be 2.87 times 10 to the negative 11th. An alternate way to find the hydroxide ion concentration, remember, is to realize that if you know the pOH, you can take 10 to the negative pOH power and you will get the hydroxide ion concentration. So if I raise 10 to the negative 10.54 power, I again get 2.87 times 10 to the negative 11. Now you can have some variance based upon how much rounding you've done. Just try to keep it at 3 significant figures as a minimum when you're working these problems. Alrighty, if you want to consult my PowerPoint, I've got several more practice problems for you on there, and I hope that you have fun with it and enjoy acids and bases. We will definitely do more with it and get into fun stuff like defining strong acids and strong bases and weak acids and weak bases, and boy, get to work on some equilibrium stuff there. And then we'll get into buffers, so looking forward to doing those for you. Hope you have a good time with this. Thanks for listening. Bye.